So can now. Let me try and share screen now. Where's the share screen button? I appear to have lost the share screen button. Okay, let me leave and rejoin. There we go, share screen. Okay, so you can still hear me, and hopefully you can also see my screen.
Yep. See in here.
Perfect. Okay, so I think we should be good to go now. That's 9 past. We've given some more stragglers time to come in. Let's just go to the course and open this up. Give it a moment to load. Yes, also apologies for all the technical errors. Thought it was going to be more straightforward, but apparently not. Okay, so this is the SNARK Fundamentals course. We did give a very brief intro on Monday if you were there, kind of unexpectedly. But just to recap, so this course it's sort of designed to try and hit this sweet spot, intermediate spot, to help people with no background at all in zero knowledge to start and to, by the end of it, they should be able to engage in conversations about ZK SNARKs and have a basic understanding of how they work. So that's going to be ideal for people who are looking to become developers, because after this course, you'll have a good idea of what's actually going on, and you can go on to more advanced courses. Or entrepreneurs, or anybody who wants to work at all related to the ZK space, so you have a basic understanding about how to discuss the topic, about where this tool can be used and what its limitations are. So this is a 4-part course, an hour and a half each session. Yeah, I think those are the main things we want to share. There is going to be some associated homework, but it's not checked. It's designed to just support your learning as much as possible, and I'll touch on that at the end. And a bit of a background as well. So I've been doing zero knowledge related topics for the past several years. I have a mathematical background, and I went and I did research and then development in SNARKs, and I did a lot of education related stuff. And so, yeah, this is something we're quite interested to see. I wrote all the content with Kichong. It's been a very nice process. And now we're looking forward to sharing this content in more of an interactive format online and seeing how well it translates. I don't know if Kichong wants to say something about himself as well, but he works at the PSC and has been kind of the main person who made this course possible. I believe Kichong spoke on Monday and doesn't need to speak today. So I think we're just going to get going. Also, thank you to the, no need to speak from Kichong. Thank you to the Kenyan community for organizing this and joining. You guys had a lot of energy, and we're looking forward to sharing this with you. So we did the introduction. Just to reiterate in a bit more detail what to expect. Like I said, we want you to know why SNARKs are valuable. Ultimately, any discussion about the use of ZK SNARKs relates to why they're valuable and what problems it solves. We're also going to give a bit of detail as to like how it provides those valuable traits, and whether all the valuable traits that the technology provides are always necessary or always used, which is kind of a funny topic actually. And then also, the style we're doing is aside from this general learning, we're going to take a single proof system called Plonk, and we're kind of looking, when we talk about how it works, we're actually talking about how Plonk itself works. Plonks. The purpose of this is it's kind of a more effective teaching method that rather than like see everything in the space, because blockchain, zero SNARKs, they're designed in very different ways, and it's very hard to try and look at them all at once. And it works a lot better if you just take one system and kind of understand it much better from bottom to top. And then translating that knowledge to understand other SNARKs gets a lot easier. And Plonk we've chosen specifically because it's just a bit more intuitive in how to think about it. Some of the other ones, aspects of them just aren't particularly intuitive, and people complain about them non-stop. In terms of what what we'll cover in the different sessions, this first one is, what does this technology do? And actually, the core bit of learning about what SNARK does is going to happen in the first half of this session. And that knowledge that we're going to cover is, I think, the kind of base knowledge that anybody who's going to do anything with this technology should know. Everything past there is gaining more details into the inner workings a little bit, and also seeing a few other types of SNARKs or SNARK systems. In the second session, so that'll be on Monday, we're going to look at some of the mathematical objects we use in these systems. In the third session, a week today on Thursday, we are going to look at how we combine the mathematical tools from the second session to make more advanced contraptions. And then in the fourth session, Monday after next, we're going to see how those contraptions from session 3 are put together in Plonk, and then have a brief look at a few other proof systems out there. So that's the overall outline. And yeah, make sure to stop me along the way if you have any questions. I can see the chat. I've got it on my screen, so you don't have to put your hand up. You can just drop them in there. So, section 1, let's get going. The purpose here of really this first session, but in particular the first half, is we're going to try and understand this image, because this image represents all the basic things we'll want to know about SNARKs. So right now, you can see several steps. We go from the value idea to an idealized circuit, to a witness, to a proof, to checking the proof. And by the end of the first half, this picture is going to make a lot of sense to you, and the kind of distinctions for different parts. Okay, so our learning aim is to be able to understand this picture, and such that you can even draw it yourself from memory, because it just, the flow makes sense to you. We're going to start off with the idea of mathematical guarantees. So maths is built sort of on the shoulders of giants. When we prove something in maths, we can then use it in future 100%. And we started this system with a few rules that we called axioms. These axioms were never proved or anything. We just said, if we assume these rules to be true, what will happen? So in maths, we have a few axioms that we assume to be true, and then we can define some objects, and then we can just play around with the objects and see patterns of behaviors that will turn into theorems. So I'm going to explain the relevance of that, but I'm going to give an example, a particularly interesting example to start with. And there's this book called Euclid's Elements. I don't know if any of you have heard of this book before, but it was, okay. Someone's asking if we've lost audio. I don't know if that's just Ochieng or anybody else as well. Okay. Okay, so I'm going to assume that's on the other person's end, just for one person. So I'm going to continue. So Euclid's Elements is actually a particularly fascinating book in, like, I know, the history of all science and stuff. So it was written around 2,300 years ago by somebody called Euclid. There's a bit of discussion as to whether it was he wrote it all himself or whether he combined the learnings of the time. But it's lots of people say it is the kind of foundation of modern mathematics and science itself. And that's because it follows this system I just spoke about before. It lists a few axioms to start with, just simple rules, and then it makes some definitions, and then it just plays around with them and sees patterns of behaviors and defines theorems. And this is the kind of scientific process, right? You build on the work of previous scientists, and bit by bit you grow this huge corpus and database. And I put this ChatGPT screenshot in there primarily just to show you that I didn't tell ChatGPT what to tell me. It just mentioned this book's name by itself. So up until the 1800s, it's kind of interesting. If you were a learned person, if you had learned anything in mathematics or philosophy or things like that, you had almost definitely read this book, because this book would so perfectly displayed the process of defining some rules and then growing everything in a very logical and consistent way. So we're going to look at a single example from there. So this book is actually, it's not mathematics in general, it was geometry only. And it had 7 axioms. One example of those is that things that are equal to the same thing are also equal to each other. So there's several words there, but it's actually fairly straightforward. If you have if A equals C and B equals C, then A equals B. Like if you have 2 things and they're the 2 equalities, you can transfer the property over. So if I'm 70 kilograms and somebody else is 70 kilograms, and our weights are the same as a third person, then the first 2 people's weights are the same. It's almost so simple that it's hard to describe. Like if you have 2 equalities, then the equality transfers. And then from this, we can derive a proposition 1 in the book. So on a given finite straight line, if you have a straight line that's not infinite, it's just finite, it's possible to construct an equilateral triangle. And you can see in this image on the right is a visual proof of this. If AB, the line between the points A and B, is the line you start with, you can draw a circle around A and a circle around B, and those circles have the same radius as the length AB. And then you see that point C is dotted in because it's on the intersection of the 2 curves. But because these are radius to the edge of a circle, the line AC is the same length as the line BC. And we also know that AB is the same length. So then we can use this axiom and show that all 3 of these lines are the same length, and that we have an equilateral triangle. So I know for lots of people, geometry is kind of like school maths, things people didn't like as much, but we don't need to know this rule. I'm just trying to demonstrate the principle. We start off with a basic rule. We then define some things, like we had to define a line and a triangle and a circle. But once we have them, we can play around with them and demonstrate this property, that if you have a straight line, you can always get an equilateral triangle. Now, once we have that, we can just use that again and again in the future as we please. And this is very simple, but what we're going to do is we're going to build from simple things, build up a more complex thing, but the complex thing we can just use instantly without having to think about it again. So the main reason I wanted to emphasize this is that we've been doing mathematics for thousands of years, and we built up a huge database of things we know about. And they're kind of quite complex mathematics. A lot of the stuff used in SNARKs, okay, we have another person who can't hear anything, but unless more people say, I'm just going to continue. A lot of the maths used in SNARKs is quite complex. Group theory, which is something we have, which is a big part of SNARKs, wasn't discovered until like the 1800s. It took over 2,000 years to even discover these objects. And we're going to be using them in SNARKs. So some of the underlying stuff isn't directly straightforward, and it's going to take some time, because we had thousands of years of mathematicians and scientists figuring out all this stuff, and then we're kind of making use of it quickly. But we're supposed to learn it all in a few months, what took centuries to figure out. So don't expect to do it too quickly, and you've got to keep with it in order to make progress. But also the more understanding you have of the underlying ideas, the easier the more complex stuff is. So we can get going with proof systems. And firstly, I just want to talk about the naming we use. I say SNARKs a lot, but we always write ZK SNARKs in the presentation and the book. So it's just easier to say SNARKs than ZK SNARKs. You know, a SNARK, it technically would be either zero knowledge or not zero knowledge, but we just use it as a shorthand. And are proof systems and SNARKs the same thing? They're not. A SNARK is an example of a proof system. So there are other types of proof systems, but to be honest, if they're not SNARKs, we're not particularly interested in them because their properties aren't particularly valuable. But I'm going to use proof system and SNARKs essentially as the same in this course, so be aware of that. You're probably aware that the proof systems create a proof. And what does the proof actually tell us? What the proof tells us is a kind of very clear thing. It says with 99.9999%, you know, going onwards likelihood, statement X is true. And what different proofs have are like different statements. So here's some straightforward ones. Alice is over 18 years old. We can get a proof that with 99.99999% likelihood is true, Alice is over 18 years old. Or Elif knows a secret key, or David is eligible to vote. Right? We have very clear statements, and what the proof says is actually that this statement is true. Okay? So anytime you get a proof, what it's saying is some statement is true, and we're going to look and see how we define those statements. Also, to note a distinction, in maths, when we prove things, we prove 100%. That equilateral triangle thing I said before, it's 100%. Once you have a straight line, 100%, you can always get an equilateral triangle from it. In anything that's not like deep mathematics, you don't prove absolutely. So, I mean, gravity is it's technically just a theory. There's so much evidence that it's, you know, true, correct, etc., that we don't give any thought to the idea that it's not actually right. Okay, the proofs, the statement on the previous page, it didn't say with 100% likelihood, right? It said with 99.999 and so on. So it's not a mathematical proof. It's actually a probabilistic proof. It's statistical. It's just saying the chance that this proof could have been faked is so small that we can essentially treat it as true. And how small is that error term? We decide when we make the proof. We pick some parameters, and we have, you know, standards in cryptography where we expect the error term to be so small that it will essentially never happen. Generally speaking, when people investigate this, it will take the world's best supercomputers millions, if not billions of years of processing to try and find a fake proof. So we can really just trust these to be 100%. One of the best ways to cement your understanding of SNARKs is through something called verifiable computation. It's a much better perspective on what we're actually doing. So, of course, verifiable computation, it kind of says, can we check that a computation was done correctly? So if I add a bunch of numbers together and I give you the sum, how do you check that I did the computation correctly? We know we can always naively check. You can just add together all the numbers again and see if you get the same answer as me. So that's not particularly interesting. But what an interesting question is there a way for you to check what I've done without repeating all the work? Because then that would be particularly interesting. And an example of this in the real world, a very helpful analogy, is either a Rubik's Cube or a Sudoku. If you give me a Rubik's Cube and I solve it and I give it back to you, you can check that I did my computation correctly because you can see that the cube is done correctly. You know, you didn't have to redo the Rubik's Cube in order to check whether I'd done it correctly. Similar with the Sudoku, if you hand me a Sudoku and I fill in all the things and I hand it back to you and you check that it was done correctly, you know I did my part correctly, but you don't have to redo the work. Okay? So one thing I want to emphasize there is this idea of succinctness. So in these two examples, like I said, your checking is very quick. You know, in the Rubik's Cube example, it's almost instant. You just look at it and then like you're just like, yeah, it's right or not. And you know the world record, I think, for finishing a Rubik's Cube is like 6 seconds or 4 seconds or something. So all of you can check that a Rubik's Cube was done correctly faster than the fastest we've ever finished a Rubik's Cube. So that's the idea, a part of the idea of succinctness. So in SNARK, the S stands for succinct. And the fact that you can check the proof way quicker than redoing the computation is half of that property. The other half is actually that the proof is much smaller than the computation. So analogies only go so far. In the Rubik's Cube example, the size of the proof is kind of not very clear because, you know, I'm just handing you a Rubik's Cube again. And what was the computation to solve the Rubik's Cube? Well, it was like turning the sides. So how does the proof size compare to the Rubik's Cube size? It's kind of like not a good, easy comparison to really think about. But the Sudoku example maybe helps a bit there because the computation in solving Sudoku is, if you've ever done a Sudoku before, you just go through all the columns and you go through all the rows and you go through all the boxes, checking certain rules to see if you can find a missing number. And you just repeat that process again and again and again and again. So that process of that computational work is, you know, actually a fair amount. But the size of the proof is actually just the 9 numbers by 9 numbers, like 81 numbers in total, is kind of, you can hopefully see a little bit that the proof size there is sort of smaller. So the succinctness actually has two aspects that are short. I mean, succinctness means like short or fast. So, I mean, but I've started off like speaking about different things, and it's quite like a large topic we're trying to get to grips with. So I'm bit by bit going over different parts and trying to add more clarity. We're going to do some drawing for some of the parts as well that we're going to get to soon. So right now I want to talk about, if we're verifying computation, what do we actually mean by computation? There's a variety of ways in which we could define it, but in SNARKs, we're interested in a very specific type of computation, and we're going to do that in the language of something called circuits. So binary circuits, you're probably aware, the device you're on right now, the laptop or phone, it's using binary logic. It's got zeros and ones, you know, true and false, just whizzing around wires and going through gates. And those gates are AND gates and OR gates and NOT gates and exclusive OR gates. I think there's, you know, 4 main types. And that's like, you know, it's quite a straightforward base system. Zeros and ones going through gates that do very small operations. And yet, because of that, you can see me on your screen, you can hear me, your computer does all these other things, like even the fact that it controls the screen is kind of strange. But the point being, like with this very basic system, we can do all this incredible, amazing stuff. For binary circuits, I've got an example AND gate in the presentation, and I've got the 4 ways in which we can fill out an AND gate. So the top 2 arrows represent like the input wires, and the bottom wire is the output wire. Okay, so those are the 4 ways we can use an AND gate. We're actually going to sketch some of these out, so I'm not going to dwell on that too much right now. So what do we mean specifically by a binary circuit? So in this white image, we have 5 gates put together with wires connecting them, 2 exclusive OR gates, 2 AND gates, and an OR gate. A circuit is just any combination of gates put together. A binary circuit, we're going to be using binary gates. So, you know, there's no multiplication or addition here. This is just binary type gates. So we can try and do one quick sketch. See if we get this going. So I'm going to be drawing here Let me know if it's not clear or the color doesn't particularly work, because I don't know what this looks like on your end. Or if I should write bigger or smaller. Binary circuits. Right, so we have, like I said, we've got AND gate. Going to have 2 inputs and an output. OR gate has 2 inputs and an output. There's the exclusive OR gate. You don't need to know these gates, I'm just kind of drawing them to show you. And we've got the NOT gate, which is actually 1 input wire and 1 output wire, because it just turns a true to false and a false to true. So a binary circuit is just whenever we put a bunch of these together, right? And inputs, and we can draw those outputs going together. Oops, shouldn't have done. Into, let's say, an OR gate, and then let's just NOT it for whatever reason. Okay, so this is a circuit. We just put a bunch of gates together. Right now, we put the gates together, but none of the values are decided. But maybe in our circuit, some of them can be pre-decided. 0, 1. We don't need to decide any of these intermediate wires, because once we put in the other values at the top, they're going to be decided for us. 1, 0, 1, 0. Okay? But a binary circuit is just any collection of binary gates put together and connected wires in a particular way. And is any when we have a gate, if we just have a gate by itself, let's say an AND gate, can we put in whatever values we want for all 3 wires? And hopefully you know that's not going to be true. We can just go to a sketch again. That I can just draw out the 4 AND gates that are actually allowed. I mean, I remember when I started with these, and to me it seems clear now that there's only 4 possible AND gates, but when I was learning that wasn't clear, so I'll try and make sure these are all shown. There's 4 possible combinations. We can do 0, 0, 0, 1, 1, 0, and 1, 1. And what an AND gate means is that the output's only true if both of the inputs are true. If it's only true if you have true and true. So if we have false and false, well, they're not both true, so it's 0. If we have false and true, well, they're not both true, so we have 0. If we have true and false, they're not both true, so we have 0. And if we have true and true, they're both true, so we have 1. Okay? So when we have an AND gate, we're only ever expecting to see one of these 4 possible combinations. But if we ever put in something different, we put a 1 here, this particular gate is, we'll call it invalid, because it doesn't represent what's actually allowed in a binary circuit. So that's a gate on its own, but if we were to do that here, and we put this as a 1, this whole circuit is invalid circuit. Yeah? If you say you're going to add 2 plus 3 and you give me 4, your computation is invalid. Right? So this is going to be particularly important. This is actually sort of what we're going to be checking, that the statement that we're claiming is true, that something has been done correctly, is very much related to this. So binary circuit is just any collection of those gates together. We're only allowing, or we're only going to call it a valid circuit if all the gates respect their rule for their operations. We call this a truth table. We sketch it out. So on the left image, you say input 1 is the X, input 2 is the Y, and output is the Z. And those 4 combinations I just drew out are represented here as well. So 0 is false, 1 is true. Yeah. So then we move to ZK circuit. So what's the difference between these two? It's just really the numbers we use and the logic. So ZK circuits work with different logic to computers. It would have actually, in many ways, been ideal if we had binary logic in ZK circuits, but it didn't work out that way. So we have different logic. In our example proof system that I mentioned at the start, in Plonk, which we're going to be assuming, the numbers aren't 0 and 1. I said positive here, but technically it's non-negative because we're going to include 0. It's just going to be whole numbers that are not negative up until some maximum. So 0, 1, 2, 3, 4, all the way up to 10 or to 100 or to whatever we're going to define it to be. And instead of the binary gates, the AND gate, OR gate, etc., we're going to use addition and multiplication. So do one more slide and we can sketch out what I mean by that. So previously, with the AND gate, similar scenario. So this example gate here is a multiplication gate, and it also has 3 wires. It's got 2 input wires. We generally just call the top left input wire the A in this left image, the left wire, the top right B, the right wire, and the output wire C, the out wire. I don't use that notation here, but we will in future sessions. Yeah, and the values of A, B, and C going through these wires have to be from our set, which is 0, 1, 2, 3, all the way up to whatever we define the maximum to be. So let's just do a ZK circuits. Right, we're going to take our set of numbers, and it can be 0, 1, 2, all the way up to Q, where, for example, Q equals 10. Okay, let's just do a small number. In reality, we're actually going to have Q be like a huge number, going to equal around 10 to the 70 or 80, one of those two, which if that's roughly the number of protons in the universe. So it's a very big number, and that's where a lot of our security derives from, the fact that there's so many possible numbers. So ZK circuit, let's just sketch an example one. We might have multiplication and addition, and maybe they both go into an addition. Okay, and maybe we'll preset some of the numbers. 7, 4, 1. Okay, so this is now our ZK circuit. The circuit is more about the gates being connected together in a certain way. Filling in some of the wire values is important in some circuits, but not all. And we're gonna come to an example soon that will help demonstrate when you fill in numbers and why you might do that. Oops. Similar to before, we can have invalid ZK circuits. So in the AND gate example, if you have a 0 and a 1, your output has to be 0. It can't be 1. And oops. Same here. If we put, that's a 4 and a 1 there. If we put 6 as this output wire for the plus gate, you're not doing addition, right? It's kind of gibberish. You're not talking in a logical way to us. If we put a 6 there, this is going to be an invalid ZK circuit, right? The interesting question that has been asked and kind of answered is there a way to confirm whether a circuit has been filled out in a valid manner? That if I'm given a circuit and I fill in all the wire values, can you check that I filled them all out in a valid way? So this is the translation from before. Rather than me solving a Rubik's Cube or finishing a Sudoku, which sort of makes sense, me filling out a circuit is going to be way more powerful to us, even though it sounds a bit abstract and strange in the beginning. Another way of phrasing that is there a way to verify the computation that was done by me when I filled in this circuit? So this idea of verifiable computation. Just as a quick teaser, earlier on I said that proofs say that with 99.999% likelihood, statement X is true. What the statement actually is a ZK circuit, is that it's filled in a correct way. And we're already at a point where we can give you the high-level definition of a ZK SNARK. So we can put it all together now. A ZK SNARK takes a ZK circuit, like the one depicted here in that image. The image only has a single gate, but it's still a circuit. It's kind of a very boring circuit with only one gate. Usually we're going to be working with very complex circuits, but it is still a circuit. And it has one of the values pre-filled, which in most cases with the circuits, we will usually have many of the values pre-filled. So a ZK SNARK takes a circuit, it fills in the undecided values. Also, sorry, this is the prover doing this. So we talk about the prover, the person who fills in the circuit is the prover. And the values they fill in the circuit with, we call the witness, which is a term you should probably remember because it's one that gets missed a lot, but it is very, very important. You fill in the undecided values, and then you make a probabilistic proof from your filled in circuit. That's what the prover does. And then the verifier takes in the original circuit, which in our scenario is this one in the image, with A and still undecided, A and C still undecided, and the proof, and it checks whether the proof is valid for the circuit or not. The proof says this circuit was filled in correctly. That's what the proof is claiming. Okay, so we can just go over that in a live sketch. Let's take this this circuit we just drew. Now, hang on, let me just, how does this work? Oops. Paste. So, let's get to a new place. This is the ZK circuit, do blue. ZK. This is our ZK circuit. The prover, we usually just shorthand this as a big capital P. The prover takes this circuit and it fills out with its values. 3, 7, 4, 1. Actually, let's paste this here. So we have the color scheming. 3. Now 3 times 7 is going to be 21. 4 plus 1 is 5. 21 plus 5 is 26. So the witness is those values. 3, 21, 5, 25. Okay, so the prover is taking the original circuit, filled in their values with something that we call a witness, and we're going to get out a proof. And we always shorthand proof as this little pi symbol. The verifier, drawn this a little big so it's hard to squeeze it all in. Hopefully, the verifier will take in the proof and the original circuit and they'll check it, and they'll either be happy that it's correct or sad that it's not correct. Okay? Because the proof says, this proof says, or is claiming that the original circuit was filled in correctly. Okay, at the very high level, that's what SNARKs are doing. Okay? So if you have questions here, it might be a good time. Although it might make sense, in 2 slides, we're going to do an example that will help explain, like, give a more clear use case and how that's helpful. So the question is witness a random value. The witness is not a random value. In this example, it's a random value, but that's because this circuit is kind of meaningless. Like, you know, why would you care that I multiplied 7 by some number and then added it to 5, right? So in this scenario, it's random, but in 2 slides, when I do a different example, you're going to see that the value of the witness is actually very important. And in fact, even in the next slide, I'm going to talk about that. But it's a good question. This is also going to explain. Okay, so in the previous slide, I just said that the proof will say the circuit was filled in correctly. And yet the next thing I'm asking is, what does a valid proof actually tell us? And all we're doing here is kind of taking a perspective change. The proof is about verifiable computation. We're checking that you filled out the computation correctly. But of a more interesting perspective many times is that the person who made the proof knows a valid witness to make the circuit valid. Okay? A different perspective here is not that it's been filled out correctly, it's that the prover knows how to fill it out correctly. And again, in the next example, you're going to see why that perspective change is important. But it also explains the naming of a SNARK, because the arc bit at the end of SNARK stands for argument of knowledge. And so the proof is arguing that this person knows a witness specifically. That's what the argument of knowledge is, that the prover knows a witness. And also, when the verifier checks the proof with the circuit, the verifier doesn't learn the witness. You know, that's not passed on in the information. And that's the zero knowledge aspect. So in the Sudoku example, when I give you the Sudoku answer, you learn the answer. But in the Rubik's Cube, like if I hand you a filled in Rubik's Cube, you don't know how I did it. I mean, like maybe you do, but you know. The point being, the how to solve a Rubik's Cube isn't passed on when you see a filled in Rubik's Cube. Okay, so we don't need S and the arc from SNARK. For Elo's question, it's very good asking why we only use addition and multiplication and not division. We're going to cover that properly in the second session. But the short answer now is that because of the mathematical objects we work with, you can do division using a multiplication. Okay, naively right now, you can think that instead of dividing by 2, you can multiply by half. So we're going to do something equivalent. But like I say, we'll do that in more detail next session. So we don't want to dive into too much of the maths in this first session. We just want more the high-level overview of how the system works. And so this is the example I wanted to talk about. I'm going to sketch this out. So ZK SNARK example. I am assuming a little bit of knowledge on your end. I will try and go over it quickly. Hopefully, you're aware that if you have MetaMask, any crypto wallet at Binance or wherever, You have two very important things. You have your secret key, and you also have your public key. Okay? Whenever, if you want someone to send you Ethereum or Bitcoin or whatever it is, you send them your address, your wallet's address. That is your public key. Yeah? So hopefully this is all new to you, just in case some people don't know it, and just to refresh the memory, I'm going over it. The secret key can be used to make the public key. Right? We can go from the secret key to the public key. Now, the reason that when you have money in your wallet, it's kind of like associated with that public key. And the only reason why it's your money is because you know the secret key. If anybody else knew your secret key, they can spend your money. That's why we have to be so careful with our secret keys. It's either just like a long number, like a hexadecimal string that you might have written down somewhere as a backup, or it might be 12 or 24 words. Those words are actually used to make that long number. And that long number is used to make another long number called your public key. Okay, so hopefully you know that. If we have a circuit that does this process, so secret key to public key conversion. I'm drawing this as a box. Of course, there's a lot of stuff going on here to make this conversion, with a secret key going in and a public key coming out. But this we can represent as a zero knowledge gate. Sorry, not gate. Circuit. In the same way that binary circuits can do everything that your computer can do, just ones and zeros and AND gates and NAND gates, we can make this conversion from a secret key to a public key using addition and multiplication and numbers between 0 and Q. Okay, so if that's our circuit, but instead of the public key coming out, like right now, none of these wire values are filled in, but I'm going to fill in one wire value, and it's the output wire value. If I put that the output is Satoshi's public key, Satoshi Nakamoto, probably mostly aware, is like the founder of Bitcoin. He kind of, came up with the idea of Bitcoin and made it happen and made it. It basically started the whole industry. And there's like loads of money in his account. Right? If we have this as our ZK circuit, oops. This is our ZK circuit. And let's say I take this circuit, I take it, and I put in my witness, and I get out a proof, and then you guys take the proof and the original circuit, and it checks out. What, that was the process of what SNARKs do. If the proof checks out, what does it imply? Well, one of the first things it implies is that I did this computation correctly. This has been done correctly. But the other perspective that I told you about is that it tells you I know something, and it tells you I know, most interestingly, I know the secret key. I know Satoshi Nakamoto's secret key. Okay? So here a proof is showing you what I know. Of course, this is a very bad way to prove that you're Satoshi. Like, this is still not how you would do it. But the value of these proofs relate to the real world. And the important thing is actually, what does a proof passing tell you? Now, the fact that I was 14 when the Bitcoin white paper came out probably means I'm not Satoshi, right? So a more reasonable likelihood, a suggestion about me being able to give a passing proof is that maybe I got this proof from someone else. Maybe I figured out who Satoshi was and hacked his stuff or whatever and managed to find his secret key. Or maybe I just brute force, guessed his secret key. That third one is, again, based on the security levels we take, just never going to happen. I mean, actually, it can happen with quantum computers, but we're not quite there yet. So the value of the proof relates to the real world. And I'm probably not Satoshi. I probably didn't crack his password. So if this scenario happened, either I got the proof from somebody else if I didn't make it in front of you, or I figured out who it was and managed to hack his stuff or her stuff or their stuff. Okay, so there's a more walkthrough of a whole proof example, like what the process looks like, and then some of these ideas of verifiable computation and that I know something, an argument of knowledge, and the witness. To talk about proofs, we usually use idealized circuits. What I just drew, this box is an idealized circuit. I'm just drawing a box and saying it does this thing. And that makes speaking about circuits, ZK circuits, much easier. Because, of course, an actual ZK circuit is like tons, and in fact, usually it's millions of addition and multiplication gates connected together in various ways. Different proof systems use different gates as well. So, but we can't talk about millions of gates. So we just talk about the purpose of what a circuit is supposed to do. But that also introduces a small kind of error. As, for example, people sometimes talk about a circuit that is just you can't make. It just doesn't actually exist. Or that it's just overly complex. So at the start, I gave a few examples, such as that Alice is over 18 years old. What computation can I do that proves, or that Alice can do, that proves she's over 18? Right, but you can't do that in a computation. You actually can, but you've got to add more external stuff. What you have to do is you have to get a government agency to make a list of everybody and their ages, or a list of everybody over 18. And then Alice will prove that she's in that list, or that her age on the list means she's over 18. But then the computation relates to something that like a government agency did, and it gets a lot more complicated. But generally speaking, we can only make proofs about things that relate to computation. And if the thing you want to compute doesn't yet exist, maybe there's a way to get it built. To Fran's question, does the verifier receive the witness? They do not receive the witness. That's the zero knowledge aspect. The verifier receives... the verifier receives the proof and the original circuit. I've drawn it here, but when the verifier goes, they get the proof and they get the original circuit. And the witness here with all these filled in values doesn't go to the verifier. I think I can mention this now. You can send the witness. What happens if you send the witness is you lose the zero knowledge. Okay? You can send the witness, but you lose the zero knowledge. And one thing I mentioned before, ZK SNARKs have two really important properties. One is this succinctness. Oh, was that? One is this succinctness that checking the proof is really quick, and then the proof is quite small. So that's really important because you can speed up block time. Anything that requires lots of computation, you can then make much smaller, and you also get zero knowledge. But there's a lot of real-world use cases where, because of like consensus designs and design and things like that, it's very hard to get succinctness and zero knowledge. So what they do is they'll just use the the succinctness property, and they'll just reveal it. They'll pass the witness. They won't maintain the secrecy. But that's still a very useful way to use the technology. Unfortunately, it's often badly named because these things will be called like the ZK EVM or ZK this and ZK that because the technology is called ZK, zero knowledge. But zero knowledge is only one of the two properties, and the ZK EVM doesn't use the ZK property, it uses the scaling property. So yeah, be cautious of that. But in general, the verified doesn't need to receive the witness. So I spoke about these idealized circuits, and that sometimes we just talk about proofs that we can make, circuits we can make, but they're just unwieldy. They'll just take years to prove, or like minutes to prove, or something, or literally aren't possible, or require a government agency to make a list, and we don't know anybody in the government. So that's an important aspect of it as well. Some more idealized circuits is on the left we have a voting circuit. We take an ID and a signature. We prove that we can vote, and then we take our vote option and we combine it into the aggregate result, and we get our vote data. This is another example. Like, how do you prove you're allowed to vote? In order to do that, a system like a project called MACI, M-A-C-I, Minimal Anti-Collusion Infrastructure at the PSE, it uses a smart contract before, where everybody can register and sign up on the smart contract. And this might be a DAO running or something, and like you have to have a DAO token in order to be able to access the smart contract and put your name on the list of voters. And then in the zero knowledge proof, you're going to prove that you're on this list and that you haven't voted before, or that you're changing your vote. So these get quite complex. And then on the right half is just a transaction circuit. So you take Ethereum state, you take your ID, and you prove that you have enough Ethereum in your wallet to send, and then you show that it's valid, etc., etc. But this is an idealized circuit. We can now talk about a transaction circuit in 2 words, as opposed to all the details of what it might need to look like. And that way we can figure out whether it's worthwhile to figure out what the circuit should actually look like. And then of the starting image that I showed you, we're going to go back to that, I think, in the next slide or the one after. There's one last part. And this is to go from an idealized circuit to a zero knowledge circuit when you're filling out all those gates. This process is called arithmetization. This is actually, for many ZK engineers, this is what they spend most of their time on, is turning idealized circuits into actual ZK circuits. They spend ages coding in Rust or whatever other language they're going to use, just putting gates around to represent the computation they want to use. So how do we turn that black box into the literal addition and multiplication gates with wires connecting them? Because if you don't do it correctly, yeah, you can also use C. If you don't do it correctly, the circuit's not going to do what you said it was going to do. So you've got to get this right. And also, if you don't do it correctly, it might be possible to break it. There are some zero-knowledge programming languages in C. I don't know of any in Python, but there very well might be. Generally speaking, they try and use, because proof systems are slow, they generally try and like optimize as much as possible. Right, Circom uses a proof system called Groth16. Does it use a Python backend? Maybe. That'll be a good thing to look into, and I'd love to see any links showing different languages. So just a quick recap of everything. So where we started, I showed you this image, and then going over all that stuff. We have an idea about something we want to do. Usually this is kind of the role of the entrepreneurs, is to say, what if we prove this thing? We make that into an idealized circuit. Like, you have a problem you want to solve, and then you say, what circuit could we make that would solve that problem? I want to buy alcohol because I want to prove them. So you're going to have to prove that you're over 18. You then take the idealized circuit and arithmetize it into an actual ZK circuit, which is where most ZK engineers spend most of their time making those circuits. Then a prover will take the circuit and add in their valid witness. I mean, they'll add in their witness. It doesn't have to be valid, because if it's not, the proof won't check out. And then once the proof has put in their witness, they're going to get out a proof. The way they get out a proof is that the people made the proof systems theoretically, and then some people coded them. And so now you just run a program or a function call that will turn a circuit into a proof. And then the verifier will check if the proof behaves. So they've taken the proof in the circuit. I should maybe have actually drawn an arrow from the circuit going into the check if proof behaves to make clear that the circuit is also necessary to check the proof. Okay, but this is the core of it. This is like ultimately what ZK SNARKs are doing. It's just this kind of relatively straightforward step process. But yeah, making circuits is not easy. Making proof systems is not easy. And finding useful circuits is also not as straightforward as it necessarily seems. How are we doing on time? So we're like an hour in. I've got like a couple more slides, and then we're going to take a break, and then we're going to come back for the much shorter second half. What is the role of entrepreneurs in ZK space? And it's kind of figuring out what useful circuits are. So some example ones are a transaction circuit to prove that you have money and can send it. And this way you might be able to add in zero knowledge. You might be able to add in privacy such that you'll be able to send money now without people knowing it came from your account or how much was sent and things like that. Also, it might make processing transactions quicker, because rather than check the transaction, they can check the proof, which might be a lot quicker. Similar to like block times. Not necessarily block times, but checking blockchains. A smart contract circuit call or an EVM circuit. The EVM, like the PSC is doing the ZK EVM project, which is trying to build like a EVM compatible zero knowledge layer 2. And they have some very big and complex circuits. I would recommend just giving it a brief look online if you find the time. Okay, so we're going to take a break here before going back to the second half. Now is a very good time for more questions about anything we've covered so far. Are there some real-world examples for transaction? Hold on. So maybe we should say that we'll have a 5-minute break and we'll have questions in this meantime. But for people who don't want to go to the loo or whatever, I think at 15 past, quarter past, we'll try and start the much shorter second half. Are there some real-world examples for transactions? Can they be used instead of smart contracts? So I'm not entirely sure exactly what the question is, but Aztec is a project that's trying to build a privacy layer on top of Ethereum. So it's like an L2 that has private transactions. So it uses ZK SNARK specifically for that. Alio is a layer 1 blockchain that is building zero knowledge transactions. And there's also kind of 2 levels to this privacy. So the first level is that you make it invisible, so that now rather than when I send you money, right now people can see that my account, they might not know it's mine, but they'll know that this account sent some other account 3 whatever, let's say Bitcoin. You can add privacy in 1 layer or 2 layers. If you add it in 1 layer, now people will just see that a transaction happened. They won't know where it came from or where it went, or what was sent, or how much, which is already a lot of privacy. And then you can even add in a second layer of privacy, and this is that on the blockchain, you won't even know that it was a transaction that happened. You just see that something happened. It could be a transaction or a smart contract call or something else, which is a pretty insane level of privacy. Another interesting example, there's one of the original privacy coins called Zcash, designed primarily just as like money and not smart contract functionality. It was like hidden money, but interestingly, they had a bug in their system, so like people could just make free money as much as they wanted. And like, if that happens, there's not even a way to check, because it's like all private and hidden. You can't even see that they made loads of free money in the system. You would see it indirectly by just like more transactions happening and things like that, as more of it's being sold. So it would that would have an effect that would be noticed, but you can't see it directly. And that was actually figured out by one of their people who worked there, because he was going to give a talk and he's just looking over the maths again, and then he just saw like it was literally just like one letter difference that was just like a small mistake, and he realized that it like completely broke the whole system. And then they had to quietly like message each other on Signal and try and be like, okay, how do we get past this? And then they had to like figure out how to fix it. They had to write the code for it, and then they had to get all their nodes and stuff to update all their code without telling them that it's broken, because otherwise the price would have crashed. It would have been, hugely problematic. Apologies for a minute. I can't remember what the recommendation is referring to. If you could give me a bit more clarity, I could try and repeat what I might have said. Validity proofs. Validity proofs are a different technology. I haven't looked at validity proofs in some time. I believe they're just a different technology and not related to the ZK at all, even though they try and achieve the same properties. I would have to check over that again in more detail. Any math prerequisites that would greatly aid in mastery of the content. Also mind sharing the languages mostly used in implementation of these proofs. So mathematical prerequisites, we're trying to have this be that you can come in with no mathematical background. But that doesn't mean it's not going to take work on your part. Oh, sorry, it's already 1:15, so we'd start by now, but maybe another 5 minutes to answer these questions. That doesn't mean it's going to be on your part. Easy for you. Like the maths that we go over in the second and third section. Like I said at the start of this session, we've been figuring out this stuff, or not we, like mathematicians, for centuries and millennia, and just built up this huge corpus of mathematics. And we're using some of the complex ideas from math to build an even more complex idea, which is a proof system. So the more mathematical maturity you have, just comfort working with numbers and things like that, the better. But there's no prerequisites per se. If you've already seen things like groups and fields and polynomials, elliptic curves, it would be helpful. You'd have understand things a bit better. But we're going to go over the definitions of each of those in the next section in a bit of a rushed, hand-wavy manner. But hopefully it should be enough for most people to get a basic grasp. And for the languages that most people use for implementations, Rust is a very popular language because it's very nice to work with and very kind of memory safe. There were a bunch that were done in C before, but it's becoming less popular. I believe Go is also used for some of them. Circom's possibly in Python, apparently. I can't remember exactly what it's in. Those are the most popular ones, I would say, Rust in particular. And so for the last question, when people talk about layer 1 providing more security, this is generally not to do with zero knowledge aspects at all, I don't believe. I mean, one of the examples I gave earlier, that Aztec is a privacy layer on Ethereum, so it's layer 2. In many senses, Aztec is more secure because there you can do stuff privately. I believe the security relates more to just ability to possibly hack the system and other general things. It doesn't really relate to revealing data about your transactions. Okay, I'm just going to see if Kichong's asking a question, and if not, I'm going to continue with the second half, which I said is a lot shorter than the first half, and also we begin to see a little bit of the maths. Yeah, thank you for that, Kichong. Kichong shared the link to the material. Apologies, I didn't share that at the beginning. I had assumed that it was available to all of you beforehand, but I really should have put that out there. So in this section, fortunately, the mini book we've written has 8 subsections, and each core lesson is 2 subsections. So the first two subsections in part 1 on the online material is what I've done today. And part 2, the next 2 lessons, is all about the maths. So I'm just going to get going so that we don't overrun too long with this second half. And the reason why in this first session is very unequal halves is because we start to get into some of the math, and it didn't really make sense to split without finishing the SNARKs, just so that we could have equal time. So a lot of what happens in SNARKs can be viewed through the lens of polynomials, making them and then doing some things with them and then checking what we did with them. A polynomial, it's kind of a scary word, but it's actually not too complicated. It's any sum of algebraic terms that have integer power values. So again, more scary terms. Let's just quickly sketch that out. Okay, I'm going to pause just to answer Alex's question, because we didn't actually answer the n in the SNARKs. It is important, but it's just kind of like almost assumed. The n stands for non-interactive, and what that means is that you can share proofs and people still believe the proof. For example, in the Sudoku example, when you give me the unfilled out Sudoku or Rubik's Cube, and I give it back to you, you saw me do it and then give it back to you, you know that I have done it. But if you hand that to somebody else and say, Errol did that, they didn't see me do that. So they can't actually be sure that it's true. And suddenly the proof's validity just vanishes. But the proofs we make in SNARKs, we can share these online and they're still valid. So that's what the N is, the fact that you can like share these proofs and you don't have to be present when they're made in order for them to be valid. Polynomials. Okay. So probably like most functions you would have used at school are polynomials. They're just sums. So, 3x squared plus 8x minus 5. This is a polynomial because we're adding powers of x, and that's kind of it. And we can take this as far as we want, 7x cubed, and we can just keep going as big as we want. They're going to be as large as we want. What we're not allowed to do is use like a square root, which is the same as like a half power. We can't use any power of x that is not a positive whole number. So f of x equals x to the 1.3 is not a polynomial. Neither is f of x equals x to the minus 1, which is the same as 1 over x. Right? Because the minus 1 is negative. We have to have positive whole numbers. Okay? And that's kind of it. But we can just keep making them bigger and bigger by extending them with higher powers of x. We can also represent any data as a polynomial. So a quick live sketch again. The numbers don't really matter. If you have 7, 41, 180, let's just say we have 3 numbers. We can always represent this as a polynomial. We can get f of x equals 7 plus 41x plus 180 x squared. Yeah, and if we had more numbers, if that wasn't there, 50 plus 50 x cubed. We can just keep adding more numbers to our polynomial, right? So we can represent data in polynomials. And why we might want to do that is because it gives our list of numbers more like properties we can play around with. And here's one of them, and it's going to explain a lot about the succinctness. With a polynomial, we can evaluate it at a number. So for example, we could evaluate this at, I should have chosen some smaller numbers, so let's just do 2. We can evaluate it at 2, in which case we get 7 plus 82 plus 720 plus 400, which sums to, what we got, 1120, 1200, and I believe that's 1209. Let's just pretend that is right. We have turned a list of 4 numbers into a single number, right? Can we go back? Can we take the single number and go back to the 4 numbers? Not really, no. But we've compressed massively. This is where a lot of the succinctness that makes proofs so fast comes from. This list, like I said, it can just go on 50, 70, 1, 5, 9. We can take tens, hundreds, thousands, millions of numbers, put them into a single polynomial, and then we can evaluate that polynomial and get out one number. So we can really compress loads of stuff together. And we can't get the numbers back, but this number we call a commitment. Once we do that evaluation, it forces us to be stuck with that polynomial and doesn't let us change it. And this is really like where a lot of that succinctness comes from. Also the hiding property, the zero knowledge. Like we can't go from that number back to the previous numbers, so we hide a lot of stuff there. Yeah, well done, Fran. So the witness is, we can think about putting it into a polynomial. We're actually going to dive into that now. The last thing we're going to do is that image we had before, I've just extended it with a few more steps. Rather than go from a valid witness to a proof, we now have 3 steps in between, which is to make polynomials and then commit to them and then query them. So we're just going to do this example. And I think basically we're done. So how do we go from a circuit and a witness to a polynomial? Is our first step. So I'm going to try and draw this out. 3, 7, 1, 5. Let's just try and 3, 7, 1, 5. And then I think we had an addition below. So that's 21. That's a 6. And that's 27. So when this is our filled out circuit, we're going to make 3 polynomials. And in Plonk, what we're going to do is going to make them for the left wires. So all the left input wires. So that's this 3, this 1, and this 21. So we call this I'm going to do L of X. It's got, the numbers are 3, 1, 21. And just to bring in the witness, maybe 3, 7, and then actually 21, 5, 6. Basically, most of these would be part of the witness. But we don't directly put the witness in a polynomial. It's kind of broken up into these different parts. So we turn the left wires into a polynomial. So this is going to be 3 plus x plus 21x squared. We're going to have the right be 7, 5, and 6. 7, 5, and 6. So 7 plus 5x plus 6x squared. And then we're going to do the output y, which is 1, 6, and 27. And so this is actually the r of x for the right. And this is going to be 21 plus 6x plus 27x squared. It's going to be the O of x for output. output-wise. I just want to talk. This bit here might have been a little confusing because this is necessary because it could be. How do we actually know that the output of this add wire is the same thing that goes into? Okay, so add here. How do we know that these two wires are actually connected? One way we solve this in the proof system is we put them both into two different polynomials, and we're kind of going to check there that the values are consistent. Because you can say you get 6 out, but then actually just chuck in a 7 into the next proof system if you're not careful. So we've got to account for that somehow. But this is how we commit ourselves to. Sorry, that's how we make a polynomial from our circuit. For Clinton's question, why the 26 7 different coefficients? So I'm going to ask for a bit of clarification. Coefficient 27 is called the coefficient of x squared. But the reason why 21 has no x and 6 has x and 27 has x squared is a distinct position in the polynomial. We don't want to mix them together. But if that wasn't quite your question, please feel free to ask again. So we've made our polynomials from our filled-in circuit, and then we can commit to them. So the green when we commit, we'll actually do them at a random number. So in the proof system, we have to get a random number from somewhere, which isn't something we really cover in this course because there's just so many details of things that have to be there. But we get a random number and we put it in. And let's say it's L of 4. So we get 3 plus 4 plus 16 times 21. 320, 336. We've got 340, 343. And these are actually going to be the same number, same random number. So R of 4 is going to get 7 plus 20 plus 16 by 6, 96. Going to sum to 123. And then the last one is going to be O of 4. Yeah, it's just getting a bit too big. 21 plus 24 plus 16 times 27. You're going to get out a single number. Okay. But now we've sort of committed ourselves to this circuit in many ways. In the next session, in fact, in the third session, we're going to go over a little bit more detail to this picture here, because once we commit and we make these values, we're not going to be able to change our circuit here. In particular, it's the witness we're not really going to be able to change. So we make them, we commit to them, and then we actually make some more polynomials in various ways. We might go over that a little bit in section 4 in the fourth lesson, and then we can query them. So there's a lot of stuff going on with polynomials here, and you've seen that we can compress a lot of stuff with polynomials. So you've seen how we can make them and then commit to them. The querying, it just refers to taking a polynomial and evaluating it somewhere. So yeah, the committing and querying are kind of quite related. Okay. Recap again, and I think this might be the last slide. There might be one or two after this. We started off with this first picture that we said we were going to want to understand, and then we added in a few more steps for polynomials, which is that we take our filled-in circuit and we can make polynomials from it. and then we're going to commit to those polynomials, and then we're going to like check that the polynomials were valid. I can start to describe, but because there's a lot going on, it will get a little bit too complicated and forgetful. And then we get out a proof. But this first picture is like a very, very good high-level understanding of what SNARKs do and how they can be used. So then you can start to engage in discussions of like where to use them and what might be possible. Of course, the more understanding and knowledge you have about useful example circuits that are out there or proof systems or what others have done, the better it will be. So there is some homework as well that we can get to, but of course now is the best time to stop and see if there are any more questions from that second half, or also even the first half, just any questions overall that people have. And yeah, they don't have to be. You are free, of course, to come back to there's a channel in this server called SNARK Fundamentals. If you scroll down close to the bottom, I believe you'll find it. You can always ask questions there, and whenever I see them, I will get back to them as soon as possible. Of course, it will be helpful for you to look through and read the online material in the interim before the next session. If you read it before the session, it's like even better, of course. And this is supposed to be 90 minutes. We're going over a little bit, so I don't want to keep people too long. So as questions come up, I will answer them, but I'm also going to try and get to the homework when there's a pause in questions. And Gi-Chong very helpfly posted the link to the. Oh, is this a different channel? Intro to SNARKs. Yeah, there's actually in this server, there's going to be many places to ask questions about SNARKs. For your homework, this is also a little bit experimental. I'm going to ask you to make to download. It's free, completely free. A software. It's free on computers. A software called Anki, which is a retrieval practice and space repetition system. And I'm just going to go over in a couple minutes why that is the best thing to do. And it's encapsulated by the bottom sentence here. So ignore what the actual task is. I'm going to come back to that at the end. The biggest problem that I see again and again and again when people learn this stuff is that they read the stuff, they get it, they kind of understand it, and then 2-3 days later, it's gone. Like, you know, your graph on how well you understand it, it's like you kind of got it, but the moment like a bit of time goes, your understanding like gone out the window, and you come back to another discussion, and they'll speak about something that was mentioned last lesson, and you just kind of can't follow along. So this homework is specifically designed for the biggest problem I see again and again. And the reason why I'm trying to battle that with this thing called Anki is I'm going to show you the science on this very quickly. This is just, I'll come back to this afterwards actually. This is what the website looks like, ankiweb.net. This is what it looks like to make a flashcard. I'll come back to that afterwards. But in this top left image is called the forgetting curve. Like scientists started studying this, I think, early last century. This guy, I think it was a German guy, he decided to do an experiment, and he decided to try and remember a bunch of gibberish nonsense phrases, and then he just tested his memory like 1 day later and 3 days later and a week later and a year later and stuff like that. And he saw that like within a few days you forget like almost most of what you learned. Like 80% is gone within like 3 days, which is like pretty bad, right? And so if you're trying to learn a complex topic, you can't just look at it once and then go to the next lesson. It's going to be gone, because like I said at the beginning, you're supposed to build up your knowledge, and if you build it up and then it gets all crumbles and you go to the next lesson, you can't build. You're supposed to build it from where you were. But then called space repetition. So you learn something and you forget most of it within a couple of days. But if you revisit the stuff in this top right image, you see that you kind of go back up to 100%. And each time you revisit the material, it takes you longer to forget. if you might forget one day, but once you see it again, it will be 3 days, and then it'll be a week, and then it'll be a month, and you can really grow your memory, help remember stuff long term. And at the bottom is another study where they gave people 4 scenarios. So like they got them to study something, or they got them to do repeated study, or they got them to do concept mapping, which is first they studied and then they drew like mind maps to kind of help solidify their understanding. And then in the last one, they got them to study, and then they got them to like practice retrieval practice, which is essentially flashcards, which is what these 4 columns are. Now, in the left graph, it says verbatim questions, and these are literal questions. This is where people learned, what the definition of a SNARK is, like what does the acronym stand for? Succinct, non-interactive argument of knowledge. If that's what your flashcard is, and then they tested them exactly on that question. And you see that retrieval practice is like far ahead of normal study and repeated study and concept mapping. Like there's really no comparison. It's really, really far ahead. The next one is inference questions. And this is that like you learn A, and the question isn't A, it's like something that happens because of A. You got to like use the knowledge you have to figure out something else. And you see again that retrieval practice is like still better than the others. There's not as clear as a lead as the other ones before, but it's still like far ahead. And compared to just study once, so like if you just come to this session and then you don't do it again, you're going to be in this red graph where like the amount of questions you can answer afterwards is going to be pretty bad. And for people who do additional practice, they're going to do a lot better, of course. And this third graph is really interesting. It's called metacognitive predictions, which is really like confusing. What it actually is they ask the people, which of these 4 learning methods do you think will be the best or the worst? And very ironically, people thought retrieval practice was going to be the worst one, which is almost insane because the retrieval practice setting was they had to study and then do retrieval practice. And people thought it'd be worse than just study. So like, there's a lot of misunderstanding about the effectiveness of retrieval practice. Okay, so that's why the homework I'm trying to give is specifically for this issue to help you remember as much as possible, because we are really building this stuff up. And if you come to the next session or sessions and you can't fully remember some of the stuff before, it just becomes very hard and very uninteresting to try and follow along. So what does it look like to use Anki? You make flashcards. This is the example of me making a flashcard. On the front of the card, I ask, what is the gas cost of verifying a Plonk proof versus a Starkware proof on Ethereum? Okay, and on the back, I put my answer. And then I also put some context for myself in case I forget where I got this from or it's wrong or something, I want to go back and change it. When I make that card, then when I review it, Anki will just show me the front of the card, and I'll have to try and remember the back. Anki doesn't tell you well done or anything like that. It's just about you and how well you decide you remember something. So you see the front, and you try and remember the back, and then you'll click, and it will show you the back, and then it will give you 4 options, 1, 2, 3, 4, like easy, medium hard, or hard. And then once you click one of those options, an algorithm will decide when to show you this card again. Should it be tomorrow? Should it be in 10 minutes? Should it be in a week? Should it be in a month? And it starts off from like 30 minutes, and then it goes to like a day or 4 days, and then a week and a month. So it quickly, the interval goes up very, very quickly. And these algorithms are scientifically engineered to be as efficient as possible at getting small bits of data into your long-term memory. Okay, so this is going to be one of the best things you can do when we're learning SNARKs, particularly in the beginning, to get your head around a lot of these definitions. So what is the actual homework, aside from downloading it and installing it? If you can make cards on some of these things, it will be very, very helpful. At the end of the first 2 subsections, we have kind of a glossary, like a very short glossary, with lots of the keywords we use in this talk in that section. If you can make cards on those, it would be very, very helpful. And then you can add in as many other cards as you want on any example that you want to try and remember or things. And it's generally best if you write the cards in your own words. You can copy and paste bits and pieces, but one of the helpful things is that by writing like trying to solidify your answer to a particular question yourself helps you learn it very well. And try not to make cards too big. Like the example I just showed you with this gas cost is like a very actually straightforward answer. You know, there's not like 3 paragraphs explaining loads of things. You can't, that's like not a small snippet. You want like a small snippet of things to remember. But you can test yourself to see how to make it. If you can, if you've got lots of time and really want to do this stuff, if you make cards in the next session, it would be really, really good as well. And try to do Anki ideally every day, but you know, not everybody has time for that. Every couple of days, 2 or 3 days is pretty good as well. Because again, the science is you want to look at this stuff often. It doesn't even have to be long. You know, you can spend 10 minutes and go through as many as you can, and just reinforce that understanding. Yeah, and just try and make cards for any part you really struggled with. Okay, so that concludes our first session. Thank you very, very much for coming. I hope you learned a lot, and we're looking forward to any more questions. Again, like I say, you can put them in the SNARK Fundamentals chat or the Intro to SNARKs link that Kichong has dropped there. I'll try and answer as soon as I see these questions come about. And the next session will be on Monday, the same time as it was today. And in that one, we're going to get going with some fundamental mathematical definitions, items, objects we're going to be using. Okay, but yeah, you've got the core understanding now. Thank you very much for your time. And I'll stick around for some more time if people want to stay and ask questions as well. But if not, then have a good weekend. By the way, if you have any feedback about the content in particular, but also the online sessions, it will be very helpful. You can just ping me directly in Discord, or maybe at the end we'll try and do a form or something, feedback form. But of course, we want to improve this material as much as possible.
Hi, I have a few questions. I was a little bit late, so maybe you did mention it, but I wasn't there to hear. So, does this have anything to do with Cairo as a programming language? Because I have been going through a bit of it, and I can tell there's a little bit of similarity. Is it the same thing, or am I just imagining because of similarity in functions and other things? And then, what do you think? Is it possible to liken this to quant programming when it comes to? I think that would go with the first question, because it would answer if only it's actually a programming of the sort. So, can we start there and then maybe pick it up from there?
Yeah. Thank you very much for your question. They are particularly relevant topics. So Cairo is an implementation language for something called a ZK Stark, which sounds like a different thing, but they're also SNARKs. So a Stark is still a proof system, and it's also still a SNARK. Cairo is just an implementation of that. So you can code in Cairo if you want to do Starks. I think Starkware are the ones who wrote Cairo. You can code in Circom, which uses Groth16, which is a different proof system. You can code in Halo 2 or Nova. There's like tons of different languages you can code in. And the properties of the proofs will vary a little bit. We're going to cover that in the fourth lesson here. One of the key differences as to why people might want to choose a Stark, which actually in my question here, in my flashcard, there's a Plonk proof and there's a Starkware proof, which is what Cairo should be making, is that, well, one difference is that a Starkware proof is a lot slower, clearly, because it's like 10 times the gas cost. But some people are still choosing to use it, and that has there's a very important reason for that. Starks we say they're plausibly post-quantum secure. What that means is we haven't yet found a quantum computer algorithm that can break SNARKs. We know as a fact that quantum computers, when they get good enough, like to a decent standard, will break Plonk, and they'll break tons of other proof systems, and they'll break tons of other online cryptography. But in most cases, we use non-quantum secure cryptography systems. And the reason is quantum secure stuff is a lot slower. And quantum computers aren't yet good enough. So why would people make the business decision to use slower tools for no immediate gain? As for whether quantum computers will ever be good enough to break this stuff, some people will say 5 years, some people will say 30, some people will say never. So it's kind of uncertain. One important thing to think about there is that everything that's online now and that is encrypted, but it's not quantum securely encrypted, can then be unencrypted later when quantum computers come about.
Yeah, so, okay, so should we then worry about incorporating the same without having to take away? Because one thing I know about quantums is that it can help when it comes to predictive algorithms. I was seeing some of the things that the finance bros were doing a few years ago, and that was like way ahead of their time. And what can be done now with the use of AI. And I don't know much about this one, but I'm thinking if it was harnessed together, then maybe you would be looking at awesome potential. I know it's slow, but the predictive measure is almost always accurate. It's 90 something score. That's pretty good. The odds are pretty good. Should we then look at harnessing both, or what?
I don't quite follow the question. To harness quantum computers and proof systems, or
Programming structure, yes.
Possibly. I'm not sure I've actually ever heard someone look into like doing a proof system using quantum logic. I mean, we're barely even at the stage of like having quantum secure proof systems. As for whether to like do a proof system using quantum logic, there might be gains to be made there, but there'll be a lot of like work to figure out if it's even possible, and if so, what they look like. And at some point, it will probably make sense, but it's not like generally speaking where people start off, because again, they just quantum computers aren't really much of a thing yet.
Okay, thank you.
My pleasure. Yeah. So just sticking around. If there are more questions, feel free. You can come on the stage, or you can just ask in the side chat. So confused. What's this? If you have questions about the Anki software, feel free to like ping me directly in the chat, as Errol or EDGD, although Errol would be better. Thanks, Givenchy. Yeah, I'm going to assume that most people here don't have any more questions. So I'm going to head off as well. Have a good weekend, everybody. Thanks for recording, Tyler, as well. Oh, sorry, Yoshing, you had your hand up. I should really, yeah. Where? Oh, I can't, because I can't see it on that one. I can only see you here. Yichong, can you help Ochiang to the stage? Maybe the approval request didn't go to him or something. What if we cancel it and then he tries again? Or we ask him directly, invite to speak. There we go. You're on stage. You are muted though if you are speaking.
All right, I'm good.
Right.
All right. Yeah. So, question. The math, the polynomials.
Mm-hmm.
Will we be using like calculators or something, or do we have to like do the old school? You know.
No. So, when you get to some of this more abstract mathematics, we can do worked examples where we'll multiply a few things out. But generally speaking, we're looking at the properties of the mathematical object. It's not like school where you just do a bunch of calculations. The implemented proof systems will be doing all these computations for us. We're just going to talk about these things in a more abstract manner. So there shouldn't be any need for a calculator, but a pen and paper or something to try and sketch out yourself to follow along could be very helpful.
Got it.
And we got another hand up. Is that hand up? Hey, Timothy.
Hello. So I have a question. Just you can correct me if I'm wrong. So the importance of SNARKs, real world importance of SNARKs is that it helps in scalability of Ethereum, like in transactions. If you want to post them on the layer 1, it's easier to verify a proof than the entire transaction. So apart from that, first of all, is that true? And then secondly, I want to ask what are some other real world like use cases or importance of this SNARK technology?
Yeah, so what you first said, the value case is that you can verify a transaction more quickly is like sort of true. So in fact, in this card here, quite fortunately, you see that the cost for verifying a Plonk proof is 300,000 gas on Ethereum. It doesn't actually get much smaller than that for verifying a proof. The cost of an Ethereum transaction is 21,000 gas. So transferring Ethereum is actually cheaper, easier. But that's for a single transaction. The thing is, this Plonk proof, you can have a layer 2, and this proof can contain thousands or hundreds or thousands of transactions within it. So then the marginal cost of each transaction goes down massively. These tools are used in a variety of places. They can also be used, like if you want to sync with the blockchain, you have to physically check all the blocks that came before and whether they're right, etc. But we can eventually find a way to just make a proof checking that, like, you know, the first 10,000 blocks were done, and that way you check that proof, which will be very quick, and suddenly you're like 10,000 blocks in, and then you can, you know, sync with the chain much quicker. There's a variety of use cases. I'm only going to know some of them, and it'll be very good if you ask in some of the other chats around here. But anywhere that is limited in some form of computation can probably have SNARKs applied in a way that provides value. On top of that, anywhere that could benefit from privacy could probably benefit from SNARKs. I think you also had a second question, right?
Yes, so at least that answers the question. Then secondly, if it comes to issue of privacy, how in real life, how will it really ensure privacy? Because we are saying we are posting something, it's on chain. Yes, the verifier might not know, but the prover has revealed the result. Or maybe you could elaborate more how it example, how it ensures privacy.
Right. So this is a particularly interesting discussion, and it's unfortunately not too straightforward. So I mentioned that some use cases don't use the ZK property at all. And one example is it's very hard to apply zero knowledge on Ethereum directly to get zero knowledge transactions. And the reason is because the way the consensus or like safety system on Ethereum works is that if you want to spend 1 Ethereum, people have to check your account and see that you have enough in there. There's not an easy way around that. So what they do is they'll just like reveal that data. So they lose out the zero knowledge, but they gain the scalability. An example of how that's solved elsewhere, there's a zero knowledge layer 1 called Alio, where I used to work. And Ethereum uses the account model, but Bitcoin and Alio use the unspent transaction output model, which means that you don't have like an account with all this money in it. There's just like transactions everywhere, and like maybe this one's mine and it has 3 Bitcoin in it, or 10 Alio, and it's not been spent yet. So what I can do is I can make a proof that I own the key to not to this transaction, but to some transaction in the entire list of all the transactions, and that this transaction is not in the list of spent transactions. So now I've proved that I have access to some amount of money and that it's not yet been spent, and that allows me to spend the money. But when people check the proof, the statement they learn is that I have access to money that's not been spent. They don't know whose money it is. They don't know which account it belongs to. So in that way, we can get private transactions. But it kind of requires a bit of a change on the consensus level of like how you maintain security. So if you designed a blockchain without thinking about how zero knowledge proofs work, it's very hard to then put zero knowledge proofs at the center of them. But if you bear that in mind as you design the blockchain, you can get it to work and allow that privacy.
Okay, makes sense. Sorry, last one. Before SNARKs, I knew there was a technology, there was the STARK. Can you elaborate the difference between the SNARK and the STARK?
A STARK is, there isn't a STARK that anybody uses that isn't also a SNARK. They try to make the distinction with the T at the end instead of the K. The T stands for transparent. What that means we're going to cover in the next sections. But they basically want to make a distinction based on one security property of proofs. And that is for Plonk, in order to work with the system, you first have to like have everybody set it up. And this is like adds in a security assumption. So I think STARKs actually came to light kind of after the innovation of SNARKs, because again, a STARK is just an example of a SNARK. But the best way to think about it is that it's just another proof system that's out there and that you can choose from. You can use Plonk, you can use a Stark, you can use Groth16, you can use Halo, you can use Nova. There's Marlin, there's tons and tons of proof systems to choose from. And Starks are just another kind of subcategory of SNARKs.
Okay.
Cool. Okay, I'm actually heading off now. Take care, everybody. Bye-bye.